In the last unit, that is unit 5, we discussed about cylinder. In this unit, we will derive the equation of a cylinder whose generators are parallel to the given fixed line with given guiding curve. And then we obtain the the equation of right circular cylinder and also the equation of enveloping cylinder. Now, if we consider this to be, that is parabola, to be a guiding curve, then we have this to be a parabolic cylinder. In the case that if we have the guiding curve to be an ellipse, we have elliptic cylinder. And if we have the guiding curve to be a circle, then we have a right circular cylinder. And to obtain the enveloping cylinder, this is the procedure that is adopted. That is, suppose we are given a surface. Say, for example, if we are given a sphere, then we consider a line touching the surface, and if we consider the locus of that, that is, this line moves on the surface. When it moves on the surface, we get a cylinder. So that is called the enveloping cylinder. So we have the definition of a cylinder to be, it is a surface generated by a straight line which is always parallel to a fixed line. So it is the surface generated by a straight line which is always parallel to a fixed line. Okay, and any plane which intersects the cylinder whose equation is of second degree is a conic. So when we consider this, we get a conic. So that can be either a parabola or ellipse or even a circle. This conic is called the guiding curve. Now the line which passes through the centers of such conics is called the axis of the cylinder. So this is called the axis of the cylinder. We have this, and the axis of the cylinder is always parallel to the generator of the cylinder. So we have this to be a generator. This anything can be taken as a generator. So that will be the axis will be parallel to the generator. And we have the definition of a right circular cylinder to be it's a right circular, it's a cylinder whose guiding curve is a circle as seen earlier. Then we have now the enveloping cylinder, the definition, the locus of a line which is parallel to a given line which touches a given surface is called an enveloping cylinder. So the locus of this line, okay, it has to touch the surface. So the locus of that will give a cylinder, and that's called an enveloping cylinder. Now we will do problems under if we are given a generator parallel to a line and a guiding curve, then how to obtain the equation of the cylinder, for which first we will have this bookwork in which we obtain the see the procedure to find the equation of the cylinder. Now to find the cylinder, given that generators are parallel to a line and whose guiding curve is given by this surface along with plane. So they give these two together give a conic. So once that is known, and so that will be our guiding curve, and generators parallel to a given line. Right, now we will consider x1, y1, z1 to be any point on the cylinder, and then the equation of the generator passing through x1, y1, z1 will be, see, once we know a point and parallel to this line, so DZs are known, so we can write out the equation of the generator and let it be equal to k, say. Then any point on this generator will be cross multiply, so x1 plus lk and y1 plus mk, then z1 plus nk. So this will be any point on the generator, and if this point lies on the guiding curve, it has to lie on the guiding curve, then we get this. So we just replace our xyz by this. See, we have a cylinder whose equation is to be determined. This can be either a circle or a ellipse or even a parabola, and we are considering x1, y1, z1 to be any point on it, and this line is parallel to the line whose DCs are element. So a point and DCs or DRs are known, then we can write out the equation of this. So that is what we have as this. And so having got any point on it as this, then it has to lie on this guiding curve also. So it will lie on both the plane as well as, so it has to lie on both the plane as well as the surface. So that is what that is the reason why we have this equation 2 and 3. So we'll have to eliminate k between these two. So that means from here, from equation 3 we can get k, and substituting that value of k here, we will have a relation involving x1, y1, z1. Name it as, say, sum phi of x1, y1, z1 equal to 0. Then the locus of that will give phi of x, y, z equal to 0, and that will be the equation of the required cylinder. Now we will have an example for this. Suppose we are asked to find the equation of the cylinder whose generators are parallel to. So generators parallel to a line that's given, and guiding curve is given by this. So we shall name the equations as 1, 2 and 3. So as per the procedure which was given in the earlier result, we will proceed now. We shall take x1, y1, z1 to be a point on the required cylinder. We have this cylinder whose equation needs to be determined. This is an ellipse whose equation is given by x square plus 2y square equal to 1, and in the plane z equal to 3. So any point on this, if we take it as, say, x1, y1, z1, now having known the DCs as this, the equation of this generator, we can easily write out as this. We shall name that as equation 4. Now from 4 we can obtain any point on the line, and this meets z equal to 3. So this is this one meets z equal to 3, and so therefore you can replace your z by 3. Now these expressions, when we name them as 1, 2 and 3, then by considering 1 and 3 we get x value, and by considering y and the second and the third, we get that y in terms of y1, and already z equal to 3. So that is what we have as equation 5. We have from 1 and 3 we have this, and from 2 and 3. So this is from 1 and 3, and in the same way from 2 and 3 we can get this one, and already we have z equal to 3. So we shall name this as equation 5. Now this point lies on the given curve. So we have used only the plane, and the surface is also there. So that we'll have to consider, and substituting these values in that, x square plus 2y square equal to 1. So that was our equation 2. So in that we are substituting, and this is what we have. And this is of the form a plus b plus c the whole square. So using that formula for a plus b plus c the whole square, we get this, and we need only the locus of x1, y1, z1. So by just cancelling 1 3 throughout and then dropping the suffix, we get the locus as this. Now one more. We find the equation of the cylinder whose generators are parallel to this, and the guiding curve is given by this. Now we will consider x1, y1, z1 to be any point on the required cylinder, then the equation of the generator parallel to 1 is. So if we know a point and DZs, it is parallel to this one, so that is given to us. So when we consider this line, it is obvious that the DRs or DCs are given by this. So we can easily write out, we want only the equation of the cylinder. Okay, so this one is given by equation 2 and 3, and any point on it is taken as x1, y1, z1. So a point and drs or dcs are known, then equation of this line generator is known, and any point on that can easily be determined, and that will satisfy both the equations. So when we substitute that value first in this, we get the value of r, and then having got that, again this that any point being a point on this also which involves r, that can be substituted from the r which we obtained from equation 3, and by dropping the suffix we get the locus. So that is the technique used as in the previous problem. So any point on 4 we have x is equal to r plus x1 or x1 plus r. In the same way y1 plus r and z equals z1 plus r. Now this lies on equation, and this has to meet this plane. So we have, as this meets this plane, we get this one, that is just replace your x, y, z by these quantities. So using 5 in 3 on simplification, this is what we get. We shall name that as equation 6, and this point lies on the given curve also. So replacing this we get, and that is again 5 is used in 2, and this is what we have. Name that as equation 7. Now already r value we have obtained, so that is named as 6, so that is used here, and this on simplification gives you this, and by considering the locus of that we get the required equation of the cylinder. So next is we have example 3. Find the equation of a cylinder whose generators are parallel to this line and whose guiding curve is the ellipse. So this somewhat similar to this we had in the first example, but there z equals 3 was the equation, and here z equals 0. So procedure is the same. We'll have to replace z by 0. There we replace it by 3, and here you'll have to replace it by 0. And so from here you get, so instead of x1, y1, z1, here it is given as alpha, beta, gamma. That doesn't matter. And so you have this, and this when substituted in this equation, and then dropping, here we don't drop the suffix, we just replace our alpha, beta, gamma by x, y, and z. So that on simplification gives such an equation. So that was that is your example 3. Now we'll go to the next example, where we find the equation of the cylinder whose generators are parallel to this, and the guiding curve, it's a circle in this plane, z equals 1. And so naturally we'll have to take any point on the cylinder as x1, y1, z1, and being parallel to this line, given line, -1, 2, 3 will be the DZs or DRs, and this will be the equation of the generator, and the guiding curve. So any point on that when we consider, here z equals 1, so we'll have to replace our z by 1, and then we can replace. So this is 1 minus z1. See, your z equals 1, so you have this to be replaced by 1. So cross multiplying, you get minus of this and x1 minus of that, and that is simplified here. And the same way you get y by considering this and this, and already z equals 1. So substituting that in the this equation, and then dropping the suffix, we get the locus. So next one, we have find the equation of the surface generated by the straight line y is equal to mx and z equals nx. So here the line is not given explicitly, so we can rewrite this as in this way. Okay, so x by 1 equal to y by m equal to z by n. The given line, this can be expressed in symmetrical form as this. Now, as before, we shall consider x1, y1, z1 to be any point on the cylinder. Then, having got 1 m n to be dg's at drs, then we have the equation of the generator given by this, and this meets the curve at z equals 0. So when z equals 0, you can replace this by 0, and this together gives the x value, and the same way y, by considering this and this, we get y, and z is already 0. So just substituting these values in this equation, and then considering the locus, we get the equation of the ellipse. So this z equals 0, the equation can be with y and z with x equal to 0. So procedure is the same. Now next is find the equation of the cylinder whose generators are parallel to just x-axis is given. But this is not given. We have written it. X-axis equation is given by this. That is known to us. So we shall name that as equation 1, and guiding curve is given. So we shall take as before x1, y1, z1 to be a point on the required cylinder. Then the equation of the generator parallel to 1 is given by this 1, 0, 0, d's at drs. And this one x1, y1, z1. So point and d's are known. Equation of the generator can be written. We shall take this as say some r. Now any point on this is given by, see, whenever we have this to be just z equals 0, z equal to 3, then it was very direct that we were able to get by considering first and the third, and second and third, and then taking z equals 0 or z equal to 3. But when we have such an expression, such cases, we'll have to have our value for our x, y, z, and then substitute that in the given this equation 3, obtain the value of r, and again this being a point on this, again substituting and replacing r, and then dropping the suffix, we get the locus. So that is the technique. So as this point meets Lx plus My plus Nz equals P, we get, just replace x, y, z by this. So from that you get your R value, and having got R, again the x1 plus R, y1, z1 being a point in 2, they satisfy equation 2. So we have this, and replace your R by the quantity given in 6. So this is what we obtain, and this on simplification gives you this line, and from here by just dropping the suffix, and this can further be simplified. Okay, so that will give the required equation of the cylinder. Then the next one, find the equation of the cylinder whose generators have direction cosines Lmn and which passes through the circle. Now let P of x1, y1, z1 be any point on the cylinder. The equation of the generator through PR. Lmn that's given, and when y equals 0, this is what we get, and as we did in the previous cases, x value, y is 0, z value can be obtained, and is it it's a point on this one, so you'll have to just substitute x and y value, simplify, then find the locus. To find the locus, just drop the suffix, you get the locus. Now the next one is find the equation of the right circular cylinder whose axis is given and it passes through the point 0, 0, 3. So here it is not given directly, the guiding curve is not given. So the guiding curve is not given. So in this case, how are we going to proceed? We have the equation of the axis of the cylinder. Axis of the cylinder is given. Axis of the cylinder. So this will be a problem which can be dealt under right circular cylinder. Right circular cylinder. How to obtain the equation of a right circular cylinder, which is the next topic that we are going to discuss. but here it is given. Okay, let us see how we can proceed with this. The equation of the axis is given as this. So this is the axis whose equation is given by x minus 2 by 2 equal to y minus 1 by 1 equal to z by 3. So the equation of this is given. And 0, 0, 3 is any point on the cylinder, so that is given to us. And from here we can easily see that 2, 1, 0 is a point on the axis. 2, 1, z minus 0. So 2, 1, 0 is a point, and DZs of this are given as 2, 1, 3. Right. So if we consider the DZs of this, so this is, suppose I name this as say M, and this is say Q. So what we have here is, we have the point P of 0, 0, 3, and this point we have as Q 2, 1, 0, and this point we shall take as say M. We have the point this one to be M. Now this one is the radius, that is PM is the radius. Here PM, that is drawn here, this PM is the radius of the cylinder. So this is the radius. So if we consider this from the right angle triangle, we have, by distance formula we can get what this PQ is. PQ, using distance formula, it is 2 minus 0 the whole square plus, so 2 square you have, and then 1 minus 0 the whole square, so 1 square you have, 0 minus 3 the whole square you have, so minus 3 square. So you have this to be square root of 4 plus 1 plus 9. So you have root 14. So that is our PQ. The PQ is square root of 14. Right. And then from this right angle triangle, if we take theta to be the angle between them, then this QM, is given by QP cos theta. That is given by QP cos theta. Now what is theta? Theta is the angle between these two. Now how to determine this cos theta? So if theta is the angle between two lines, if we are having two lines, if we know the DZs or rather say DRs, then we can easily obtain what is and theta is the angle between them, then cos theta can be obtained. So cos theta, if we know the DRs, so for PM we have the DRs to be 2 PM for PM. This PM is this line. This is the line PM, and we have another line, namely PQ. So we want to have this QM angle between these two. We don't want PM, QM and QP. So the DRs of QP, having got P and Q, DRs of PQ is given by 2 minus 0, 1 minus 0 and 0 minus 3. So you have 2, 1, minus 3 to be the DRs of PQ. And QM DRs are given by 2, 1, 3. We have 2, 1, 3. So this is known and this is known. So cos theta can be easily obtained. So that is given by 2 into 2, then plus 1 into 1 plus 3 into minus 3, whole thing divided by square root of 2 square plus 1 square plus 3 square, and the same way here 2 square plus 1 square plus of minus 3 square. So this gives us 4 plus 1, 5 minus 9. So you have that to be minus 9 plus 5. Minus 9 plus 5. So that gives us minus 4 by square root of 14 into 14. So this is what cos theta is. So when we consider this, again we'll go back to this right angle triangle. In this, we want to know what QM is. We want to know what QM is. What PM is. What is this PM? PM is the radius. So how to determine this radius? So if we know by Pythagoras theorem, if we know in this, we want to know what is PM. We are having what is PQ, that is square root of 14, and QM is QP cos theta. PQ already we have determined. So this is square root of 14 into minus 4 by square root of 14 into root 14. So one root 14 can be cancelled. So this is what we have, minus 4 by square root of 14. So this will be square root of root 14 square minus 4 by square root of 14 square. So that on simplification will give what that R is. So we have, when we simplify this, we get it as 14 minus 16 by 14. So when we simplify, we get that as 196, 14 square minus 16. So 196 minus 16 by 14. So that on simplification gives you 180 by 14. On simplification again 90 by 7. So that is R square. And therefore we can obtain what R is. So R square is 90 by 7. R square is 90 by 7. So if we know the radius, so that is R therefore is square root of 90 by 7. So if we know the radius, and the axis equation, radius and the equation of the axis, then we can easily obtain the equation of the cylinder. So that is actually discussed in right circular cylinder. So we have that formula. So the same problem we can, it has to be done under right circular cylinder. So we shall just go through what is given over here. We have 90 by 7 from this one. 90 by 7 is this R square. This is R square, and x1 minus any point on the cylinder when we consider, it will be x1, y1, z1. Then x1 minus 2 the whole square plus y1 minus 1 the whole square plus z1 minus 0 the whole square. When we consider that, we can take like this. We can take we consider any point on the cylinder. Radius is known. This point is x1, y1, z1, and this point is known. On the axis we have 2, 1, 0. So x1 minus 2 the whole square. This is distance formula, x1 minus 2 the whole square plus y1 minus 1 the whole square plus z1 minus 0 the whole square, plus you have that this one minus this value. This value also is known to us. So that will give me R square. So it is using that formula that we have this step. Okay, so Pythagoras theorem is used in short. That is applied to this. Okay, so we have QM square, PQ square minus QM square is PM square. PM square is known, 90 by 7. So PQ square minus QM square. QM square is nothing but QM is nothing but QP cos theta. So that is what is substituted here. So this on simplification will give us this. Therefore, the locus of x1, y1, z1 is given by this. So it is the Pythagoras theorem and the cos theta. If you know the drs, then how do we find the cos theta? So these two are together helping us in doing this problem. So these two concepts. Okay. So the next one is the last one. Find the equation to the right circular cylinder which passes through the circle. Now for the right circular cylinder, the guiding curve is the circle, that is given by this. We have a sphere and a plane. When a sphere and a plane intersect, we get a circle. Now the direction ratios of the axis of the cylinder are 1, minus 1, 1. So in this case, the parallel to, generator parallel to, that word is missing. Generator parallel to a line. So that is not given in this problem. So we are just asked to find the equation of the right circular cylinder which passes through this. So when we consider the sphere, when that is intersected by a plane, we get a circle. So when we consider the any line perpendicular to this plane, it will have its drs as 1. This is the equation. This is the equation. So 1 minus 1, 1. That will be drs of this perpendicular line. Direction ratios 1, minus 1, 1. Now if you consider P of x1, y1 to be any point on the cylinder, then the equations of the generator through P, they are given by x minus x1, y minus y1, z minus z1 by Lmn. Now this Lmn we have as 1 minus 1, 1. So when we cross multiply, we get this. So when having got a point on the line and this point lies on the circle, so we just substitute and this is what we get. And from here on simplification, we get this x1 square plus y1 square plus z1 square plus 2 times r into this plus 3r square equal to 9. And when we, this is, see, this is separate equation that we have, and the plane, the point lies on the plane, so that also we have got. This is having got a point on the sphere, we have this, and this is on the plane. So we'll have to eliminate r between these two. So when we eliminate r between these two and then dropping the suffix, we get the locus. So why it is given as right circular cylinder is because we are not using the technique what we explained in example 8 for right circular cylinder, but because the guiding curve is circle, we need to call this as right circular cylinder. So in the next video we will see how to do problems under right circular cylinder. Thank you.